Martins, and he comes to us from the California Space Grant Consortium. Let's welcome Benjamin.
Thank you for the introduction, Mr. Day. So, my name is Benjamin Martins. I'm a second-year PhD student at the University of California at San Diego, and I'm here to talk about my summer research at NASA Dryden Flight Research Center. Unfortunately for you guys, when you ask a PhD student to tell you about his research, he's going to tell you more than you ever wanted to hear. And since I have more information that I can present in 15 minutes, rather than remove some of the slides, I decided to talk faster. So try to bear with me. So we'll go through the introduction, talk about my teammates that helped me on this journey, the objectives, the technologies that were used. We'll also talk about how we applied those technologies to our particular system, the testing methodologies, and then finally the results we obtained. So before I get too far in my ramble, I want to thank my teammates, Nathan Supinay and Corbin Graham, who spent their summer dedicated to this project. I'm pleased to be presenting on behalf of the team. So when we talk about active load alleviation, what we're talking about is not reducing the amount of load on the structure, but actually redistributing it into a more efficient configuration. For the sake of our research, the more efficient standard was defined by structural efficiency, not so much aerodynamic efficiency. So what we're looking at in the current slide is the structure that all of us are familiar with when we look outside the window on our airplane. What we did was we segmented these main control surfaces into a series of shorter segments to allow for more control resolution on the wings. The eventual goal of this research is to implement conformal control surface and flexible wing concepts. So the next logical step would be to take those segments, wrap them in a hyperelastic material, and have those control surfaces morph all as one piece. This would obviously lead to implementation of the entire control surface and eventually a flexible wing concept, which can be optimized over a wide range of flight profiles. Also do dynamic event, such as gust alleviation and flutter suppression. So the objectives of this current summer, or this past summer, were to develop the platform to do this control segment active load alleviation research with, utilize a compact fiber optic strain sensing system that NASA Dryden has developed, which is actually called a CFOS, develop models to predict the aerodynamic and structural response as a result of these segmented control surfaces, and also control the in-flight wing deformations using real FOS data being fed to a microcontroller from the CFOS system. So segmented control surfaces. When I refer to conventional control surfaces, I'll be talking about the flat aileron setup that we see here. This is a SolidWorks model of the wings that we were given. And the problem with these wings is the pilot only has a certain amount of control authority, usually too large for the types of adjustments that they're interested in making. So what we did to address this was we segmented these main control surfaces into a series of individual segments capable of a higher degree of resolution. So we think that these segments can be optimized over a flight envelope, and we've actually shown that. And we believe that it's a key step to the implementation of conformal control surface design, as well as flexible wing concepts in the future. So there they are, displacing into a given orientation. So a little bit about the technology we use to accomplish this. This is the CFOS system you see in your upper right corner. Again, compact fiber optic strain sensing system. It utilizes glass optical fibers with fiber Bragg gratings. The Bragg gratings are shown in a cartoon image there on the bottom right. Essentially, these gratings are the lines that are laser etched into a glass fiber. You bond these into a structure, and when the structure is strained, the wavelength of light that's reflected from the gratings changes based on the grating spacing. So in a sense, you strain the structure, you strain the fiber, the grating changes, and the wavelength of light reflected changes. You can thus back out how much strain is in the structure. So we're using the CFOS system. It's capable of approximately 4,000 strain measurements at 50 hertz. We've tuned it down a little bit for resolution, so our research was done at 10 hertz. There's other systems that NASA currently has that use a higher number of sensors for a faster response, so you can tailor that to your application. How do we apply these to our specific application? This was our stock aircraft, APV-3, Autonomously Piloted Vehicle 3. It's created by a company called R&R. It has about a 12 and a third foot wingspan, and it's a fully autonomous vehicle. It can also be flown in RC mode with the flip of a switch. So we utilize both of those capabilities during our research. The fiber optic strain sensors, as I mentioned, they're done with fiber optic Bragg graded fibers. So they're continuously graded, meaning those lines are laser etched everywhere along the fiber, but we interrogated them every 1/2 inch. That's based on time of flight information as you shine the laser down the fiber. We have 86 feet of fiber on our 4 wing surfaces. That's left, right, top, and bottom. That gives us over 2,000 strain measurements in real time. Again, we can go up to 50 hertz with the compact pots. We're doing it at 10 hertz. And we have fiber rosettes. So on the image that you see on the screen, you have 2 longitudinal runs of gauges, and you have the rosettes in the center. Anywhere you have 3 points intersecting, that gives you 3 angles. You can get your principal strains from that. Gives us valuable information about the loading in the wing. You can also get the displacement, twist, and shape of the wing at all times from some algorithms that have been developed at NASA. So the second piece of technology that had to be incorporated into the wings were the segmented control surfaces. So on the bottom right is the stock wing prior to any modification. On the top wing there, that's our final product. So you'll see that we've segmented the wing into 22 independent control surface segments. Each segment has a corresponding servo. It's 3 inches from its neighboring servo and can move entirely independent of its neighboring servo. So I've tried to zoom in and show you a couple of the linkage and servo segments there. Hopefully you can see them, but if not, hopefully the models is beginning to give some clarity. So this is our complete system out on the flight line at Dryden. See hanging from the canoe there is the FOSS system, and you can see that we have 1 flap segmented at this point in our research. The other 3 control surfaces were left unmodified, and this is just doing our systems up check, making sure that the FOSS system was recording data properly. Unfortunately, it wasn't all fun and games, and before we got started, we had to do some analysis. So we started with the aerodynamic analysis. For the aerodynamic analysis, we used vortex lattice method and lifting line theories to predict the span-wise lift distribution on the aircraft from both the conventional and segmented control surface configurations. The plot there on the bottom right shows in red the conventional configuration predicted for steady level flight from our analysis. The green segment would be shifting load inboard as far as possible with our given configuration. So you can see how the lift load has moved to the inboard direction. You decrease the tip load. Those total loads are the same if you integrate those curves. So these aerodynamic analysis allow us to optimize the segmented control surface configurations for various flight conditions throughout the flight envelope. They also give us valuable information to incorporate into a structural model that tells us how our structure is responding to these changes in flight load. So we developed a PMAP model, ran it in NX-Nastran, and predicted how our segments could optimize the structural efficiency in flight. What we have there are steady level flight. I took the load curves from the previous slide, loaded along the coiler cord in NX-Nastran at 40 nodes, and you see the displacement and strain data. We've essentially decreased the tip displacement according to our model, about 13%, and 10% on the strain, if I'm not mistaken. So again, before they let us go out there and have fun, there's more work to be done. We had to get into the pre-flight requirements. Since the wings were so heavily modified, we had to do some static load tests. We anticipate our maximum in-flight loading to be about 2.5 Gs, so we loaded to 4 Gs for a margin of safety. The upper left figure is the discretized load zones, so we put 6 zones, broke up the predicted loads from our aerodynamic analysis, and distributed accordingly. The bottom right, you'll see the inverted aircraft loaded with sand to the 4G load. The 2 figures in the top right, I know you can't really read them, but they're the strain data that was recorded during the static test, and also the displacement that was calculated from that strain data using numerical methods. The last thing that you have to do before you can fly out of NASA Dryden is a tech brief. We actually had to do 2 of them, where you stand in front of a panel of the center's lead engineers, explain your methodologies for testing, what mitigation steps you've taken to ensure asset and personnel safety at all times. After going through the thorough review, the reward is the flight request form that you see just to the right of the tech brief slide. So here's our complete system now on the flight line. You can see the fully segmented edges. Each wing has 22 of these segments. The inboard 20 are deflected in this picture. The outboard 2 are left undeflected to give the pilot roll authority during flight. And I have a short video here that shows the complete system test. It's a cell phone video, so I do apologize. Try and bear with me. I would like to point out a couple things before we get started. You'll see the two segments in the lower left corner will remain constant at first. As I start straining the wing, the 20 inboard segments will begin to move, responding to the strain. The pilot will then give a roll command to the aircraft. You'll see those 2 outer segments move. The pilot then takes over control of all the segments. We call it mimic conventional control. where we digitally linked all 22 servos back into the original aileron and flap configurations. And then he'll give command back to the control algorithms, and you'll see as I strain the wing, you get more deflection. So the deflections are happening on a very small scale. I tried to speed the video up to make it less painful, but I don't know if it was captured well enough for the presentation. So there's the roll authority. The segments are still moving. When he stops, you'll notice that it was up a little bit higher. Now he's in conventional control. Move the flaps, move the ailerons, back up with the flaps, and he gives me back control. I strain the wings, and hopefully we'll be able to discern the movement. You can kind of see, based on the outer two, that the third flapping will start to pick up above those as I'm straining the wing. Again, I know not the best video, but hopefully you guys can visualize what's going on. So the test flights were conducted using both the conventional control surface and segmented control surface configurations. When I say conventional, I'm referring to the mimic conventional, as all the segments were already made at this time. So all the data that I'll present is from the same flight. The plane never touched the ground in between. It was simply flipping on the control algorithm and flipping off the control algorithm. We did steady level flight, pitch doublets, roll doublets, and high G steady turns in both configurations. So here are some of our results. The upper figure you see there is the acceleration, the green being the raw acceleration from the onboard autopilot from the body fixed frame. The white line is the filtered acceleration from the same data. On the bottom figure there is the tip deflection that was calculated from the strain data, and then we've also filtered that to produce the orange line. Pulling up those two filtered signals, you get the upper plot in this figure. It's just interesting to show the correlation between the acceleration in the body fixed frame and the tip deflection. If you normalize that tip deflection by the same acceleration, what you see is that we've minimized or optimized the tip deflection for all flight conditions when the control system was on. So those control system on and control system off points are timestamped by the autopilot. We know that they're exact. And this is exactly when the switch was thrown to implement our control algorithms. And so throughout the pitch doublets, the roll doublets, high G steady turn, and steady level flight, we showed an increase in the efficiency of the structure in terms of tip deflection. Just to give you an idea of how much data is being collected during these flights, this was a 30-second snippet I pulled out for 3 sensors. It's a pitch doublet sequence, and what we're looking at are, again, 3 sensors, 30 seconds at 10 hertz, so each sensor is giving us about 300 data points. If you multiply that by the 2,000 sensors we have, that's 600,000 data points every 30 seconds. You can see the resolution present in the system and the powerful tools that it will unleash on the future of aviation. So looking at just a snapshot in time, if we look at the conventional control surface configuration, the upper plot is plotting the microstrain on the upper and lower wing surfaces. So the upper is the tension side, that would be the lower wing surface. The bottom is compression, that's the upper wing surface. And then you can calculate numerically the displacement from that strain field, and that's shown on the lower plot. If I take the exact same flight conditions for the segmented control system and overlay that on the plot, you would get these results. We show about a 25% reduction in in-flight strain and 30% in tip deflection as a result of implementing our control algorithms. So our future objectives are to build a more flexible, higher aspect ratio set of wings that allow for a wider range of control of tip deflections. We're using off-the-shelf RC wings, which are very stiff. We'd also like to design advanced control architecture capable of gust alleviation, flutter suppression, and then implement structural health monitoring routines into this, which is actually my area of research, so very interested in that. And then, of course, transition into a conformal control surface material and flexible wing concepts. So perhaps what's most interesting to a lot of the directors out there is my personal reflection on the experience. Personally, the Academy jump-started my PhD research, gave me valuable contacts that I'll have professionally and personally for the rest of my life. I really can't say enough about the one-of-a-kind experience. I highly encourage any director out there of any state to send their students interested in flight research. I've been involved with the UAV team, ADVSI, on campus for 3 years. I think I learned more in that 3 months than I have in those 3 years as far as the proper way to conduct flight research, and they are valuable skills I brought back to the team. In terms of the California Space Grant, it supported me as an undergraduate. It allowed me to go to work in a lab instead of a grocery store, and for that I'm very grateful. It influenced my decision to go to graduate school. I didn't know what research was until I met California Space Grant and my advisor, Dr. John Kosmatka, so I appreciate the opportunity that it provided me. I tried to give a breakdown of how I spent my time in the Academy in case any of your students are considering going. Maybe they can look at how their time will be spent It was, again, one of the most enjoyable experiences I've ever had, and I thank everyone for their efforts putting it together. On that, I'd like to just make my acknowledgments. Of course, my mentor, Dr. John Kuzmatka, I met him about 3.5 years ago, and he's been a major influence in my life. Every professional activity I've been associated with, he's been associated with in one way or another, so I thank him. Dr. Lance Richards out at NASA, I met him about 1.5 years ago, and he's been a huge supporter of my research, and he's given me access to the CFOS system for structural health monitoring. I couldn't do it without him. Again, my teammates Corbin and Nathan, they're an integral part of the research. I just want to make sure that they're recognized, and if you guys are listening, thank you. There's numerous people out at NASA Dryden that helped with the project. I couldn't name them all. I tried to give a little list, but it's by no means inclusive. Red, thanks for being our pilot. Francisco sitting over here, he did a lot of data analysis with me. And thank you all out there. I appreciate all of your help. Thank you to NASA Aeronautics Academy, Dryden Flight Research Center, and both the Oklahoma and California Space Grant for their support of the project. And with that, I'll take any questions.
What are your efficiencies that you think you've gained with the flexible structure as far as speed and fuel savings?
So we were looking at this from a...
Repeat the question.
What are the efficiencies that we would gain in terms of fuel consumption? Is that...
And speed.
And speed. So we haven't done thorough analysis in terms of aerodynamic efficiency, so that's a difficult question for me to answer. I'm more of a structures guy. So the goal would be that, yes, we have some extra hardware in there, so we add some weight, but can we shave enough structural weight, because now we've decreased the strain state in the wing over the entire flight envelope, can we shave enough weight to increase those aerodynamic efficiencies and pay the weight penalty that's associated with the extra instrumentation? So more work to come, to answer your question. There's another academy going on this year related to the same project, and we'll be addressing some of those issues then. So, other questions?
Are you pilot?
I'm sorry?
Are you pilot?
No, I'm not a pilot.
You should.
I should be. It's very expensive. I'm a graduate student.
Okay, great job, Benjamin.
Thank you very much.